maybe some comments on how to use this. So the idea is that this is similar to the games that we played with ampere. So you see, in the case of ampere, we had the same kind of story, right? We had, say, the curl of B was equal to mu0 current density J, and here what we have is just, again, the curl of something is equal to some other vector field that we might be given as a source of the thing. So we can use the same kinds of integral tricks that we had before. So just as a very simple example to show how it goes, let's say that you've got a certain magnetic field, we'll put it pointing up like this, B, that is time dependent here, okay? And now I will ask you, what is E of t? So the question is, what is E of t? Well, what are we going to do? So we're going to try to use similar tricks to what we used in the case of this ampere situation. So we're going to define a little loop. Let me draw a little loop. So I'm going to draw a little loop like this. And what we're going to think of is that the magnetic field that we have is going to induce some electric field along this coordinate here, along the loop here. Okay, so that's my path P. What I'm going to say is that I'm going to apply the integral form of Faraday's law that I just saw here, that the integral over this closed path of E dotted into the displacement is going to be the time rate of change of flux in there. For simplicity, I've oriented my normal of the surface along the direction of the magnetic field here. I'm just assuming that the magnetic field is uniform in space, but just time dependent. So what do I get here? I'm going to do the integral P dl dotted into E. So what does that tell me? Let's say I put the origin here at 0. So what does that tell me? Let's say that my E is along phi here, and it depends on a certain radius. Interesting. It depends on a certain radius, r, that is measured from the origin here, and it's going to be in this phi hat direction here. So what does that give me? It just gives me E at that position r times 2 pi r. And now the flux itself is just going to be the integral over this surface S of B dotted into the normal to this surface. So here, this is just B of t times pi r squared. Okay, so what that tells me is that E of r is just, bt, derivative of B with respect to t, pi r squared divided by 2 pi r, okay, with a minus sign. So it's minus r over 2. With just dB, and here this is just like not a vector function anymore, it's just a constant, so I can write the total derivative with respect to t of B of t, and it's in the phi hat direction. Okay, so that's the kind of simple application of this using the same integral tricks that we used when we were using ampere. Okay, so I've got my ring. I've got the changing magnetic field going through it, therefore a changing magnetic flux going through it. Therefore, there's an induced electrical field along this this thing. Question? Well, I could change my I could change the orientation of my loop to what I wanted to. So let's say I've now put the loop along my field, and I'm going to compute the other directions. I'm going to rotate my loop in lots of different directions. Then essentially what will occur is that the components that are away from this general circumferential direction, you'll see they'll just disappear from the integrals. The other way you can think about it more easily is by thinking of the right-hand rule. Okay, so again, it's just a question of doing the things in the right order. So let's say that I'm actually putting my thumb on the B. Then right hand tells me that there's going to be something going that way, circumferentially. Conversely, if I imagine having a certain current going through my loop here, you see the current that would generate a magnetic field also going in the Z direction, in this case here. Okay, so that's how you kind of work it out from the basic geometry. Yeah, question.
So a B field like this used a B field like this? Yeah.
A changing B field in the vertical direction induces an electric field in the circumferential direction. Yes. Okay, so it's like this changes, this starts moving. Okay? Yes.
Real life now, does this have to be like a metal plate or
no?
Nothing, air, vacuum?
No. So the question is, does this have to, does this require the presence of matter in there? No. This occurs in vacuum. So the changing magnetic field, which exists as a field, we don't view it as attached to any particular piece of matter. The changing magnetic field induces an electric field, which will inherit both spatial and temporal dependence here. But this electric field is again a feature of the vacuum in which this whole setup is put. Okay?
And if you do the electric field and you change that, does it also get that?
You are like let's see, Maxwell 1865, yeah, so you're like 100 and almost 60 years too late. And we will get to this in the second hour. This is precisely the genius of Maxwell that, goes down the generations. It's exactly what we'll get to later when we talk about what Maxwell did and why he's famous for his equation. We'll get to that in the second hour. Yeah, but yes, it's the answer to your question. Other question? Yes. So here, indeed, I should probably write that R of T like this, right? So RT. Thank you. Okay, because of course these are transient phenomena, right? So I assume that my B of T is some function that will change in time. We'll have derivatives and whatnot, and these time dependencies will be inherited by the E field itself. Okay, so that's the thing. Now, there's a little trick which is called Lenz's law. It's that the reaction of a system, it opposes the change that you're trying to put in there. Okay, so what does that mean? So let's go back to this example here. And let's say that I am increasing the magnetic field. I'm increasing the flux. Okay, then in what direction is my current induced? Lenz's law tells you that whatever current you induce will try to oppose the change that you're trying to push into your system. So you're trying to increase the flux. And you've got a ring which will develop a current. but which way does the current flow? Check your, sorry. Yeah, so when you think about the developing current in the loop, if it starts increasing this way by the right-hand rule, it would add a magnetic field that way. That's not the way it goes. You want, so you are imposing an increasing magnetic flux, and the system will react by pushing back on it. So the increasing magnetic field this way will induce a current this way. Okay, so clockwise looking down. Because then this clockwise current going down creates a magnetic field which points down, which compensates or tries to compensate for the increasing magnetic field that you're externally imposing onto your system. Okay? So that's the way. The change that you have tries to work against you. And if you've not seen this in like general mechanics and whatnot, this is just a manifestation of another principle, which is from Le Chatelier's principle. And so what does Le Chatelier's principle tell you? Let's imagine that you have a potential landscape like this with an equilibrium point at the bottom. And let's say that you are pushing one way. The system will push back on you to bring you back towards equilibrium. Okay? Why? Because at equilibrium, you are at a saddle point. You're at a minimum. And by definition, all the derivatives are zero. But if you move away from the point, there will be a force trying to restore equilibrium. So you're trying to push away from an equilibrium and the system pushes back against you. That's Le Chatelier's principle. And Lenz's law, he kind of hooked onto this, indeed, because that's also the case here. You're trying to push the system one way, but the system was already in a kind of equilibrium here. Trying to change the system is working against you. Question?
It doesn't count for an unstable.
No. No, but if you, yeah, so in general, if you have an unstable equilibrium, this will be a transient situation because any perturbation will lead you to fall onto another point somewhere else. So we assume that we're in the vicinity of a kind of stable equilibrium. And indeed, let's say that we have a time-independent magnetic field with our loop. And now nothing happens. So the whole thing is not exploding, you know, nothing else. So I'm at a kind of equilibrium. But now I'm trying to push new flux through it. The system's saying, no, hang on, I was sleeping. Oh, let me go back to that. Yeah.
Yeah, constant beat field, will there be any electric force or spring?
No, and you can read it through the equation here. So the question is, if there's a constant field, is there anything happening? And the answer is no, because if the field is constant, if the magnetic field is constant, then dB dt is zero, and therefore the induced E is zero. Yeah, and that's the vector. Okay, so that's the way this thing goes. Okay. So you can look at the notes for another couple of examples on this, and let's see. Yeah, so that's the kind of idea. So in general, all the tricks that you've learned to manipulate these integral operators and whatnot can be used here in symmetric situations. Also, it can be quite simple.